Hey Precalculus, we've got a new video for you, the much anticipated 3.5 notes. This is basically going to be a rerun through all of the function composition stuff, but I think we need to practice so that these concepts become rock solid in our brains. So, without further ado, this little expression here means g of f of x. That means we're plugging in 1 over x into all of the input values for g. So wherever you see an x for the g function, you're putting a 1 over x. So the g function is 1 over x plus 2 times x minus 3. In place of the x, I'm putting 1 over x. So this is like a variation of the function. What I'm going to do is simplify that right away. I showed in class that there's a very simple way to simplify this that doesn't involve getting common denominators here, and then getting common denominators here, and then multiplying the two fractions, and then dividing. It requires none of that. So here's what you do. If you want to simplify this, I can get rid of the x in the denominator of this fraction by multiplying just this group by x. Okay? So if I multiply the bottom by x, I also have to multiply the top by x. That gives me x over 1 plus 2x. And then on top, we're going to get 1x. But I'm not done yet. What if I were to multiply this by x, which means I'd also have to multiply the top by x. So you'd get negative 3x plus 1. 1, because the x's cancel, minus 3x. And then on top you have x squared. That's your composite function. I like that. It was a quick, nifty move, and you didn't have to do a whole lot of computation. Now the question was, what's the domain of this function? Well, there's a two-pronged approach. You first have to say, what's the domain of the input function? Well, the input function cannot equal 0. So regardless of whether or not 0 is a domain issue for my composite function, if it doesn't fit the input function, then it won't fit the composite. So, in layman's terms, x can't be 0 is the domain of the original. Therefore, x also can't be 0 over there. Now make sure you consider the composite function itself. The composite function can't have 1 plus 2x equaling 0. And it also can't have 1 minus 3x equaling 0. Which means we've got x cannot be negative 1/2. X cannot be positive 1/3. And x cannot equal 0. So those are the three domain issues for this function. So the domain of the entire function can be written two ways. It can be, it's all real numbers except x can't be these three spots. For the domain, that is. Or if I forced you into a situation where you had to write it in interval notation, which I often do, you would write it as negative infinity, because there's no like even root situations that restrict your domain. Negative infinity, pit stop at negative 1/2, parentheses, because it's in the bottom part of a fraction. Negative 1/2 to 0, another pit stop. 0 to 1/3, another pit stop, and then you go a third to infinity. So one way in which to express the domain, interval notation for expressing the domain, and then here's the composite function itself. Let's talk number 2. If I can find an eraser. There we are. All right, so here's f of x, here's g of x. What happens when we put g into f? Well, g is a square root, and it's going in place of the x right here. So this composite function, not a tough one to figure out what it actually is. It's just root x plus 4 in place of the x minus 1. So here's the composite. You ask yourself, what's the domain here? Well, the input's domain must force the inside greater than or equal to 0. So right away, we know x has to be greater than or equal to negative 4. The composite function itself also, though, reinforces that concept, because if we had a root in the composite function, we would still have to do that. But we know that the bottom of this fraction cannot equal 0. And I guess technically, when we talk about the composite function's domain, we would also say, x plus 4 has to be greater than or equal to 0 because the root exists in there. But we already know that's true. This is just a formality for number 2a. Anyway, you can add the 1 to both sides. Square it. You're left with x plus 4 is just can't equal 1, which means negative 3 plus 4 can't equal 1. So there we go. We know that this function starts at negative 4 with a bracket, must make a pit stop at negative 3, but then can continue on to positive infinity with no other... Negative 3 to infinity. Oh man, that was going so well, and then I just totally flopped right there. Please forgive me. G of f of x. All right, so we're plugging a fraction into this square root. Wow. Okay, the square root of the fraction 1 over x minus 1 plus 4. Now, I think there is some wisdom in saying that this function can be rewritten as a rational function inside of the square root. So that's what I'm going to do first. I'm going to find a common denominator between 1 over x minus 1 and that positive 4. Put the 4 over 1. We need this to be the common denominator. So that gives us, can you guys see all that? Yes, great. Wow, if I got more room over here, I do. I'm going to use that space. So it's 4x minus 4 plus 1. All over x minus 1. So this right here, that's my composite. Now, what we do to determine the domain of that is we consider the input. The input has a domain issue at x equals 1. So we know right off the bat that x can't be 1. Similarly, you would do a root here. You know it has to be greater than or equal to 0 because it's underneath the square root, which we talked extensively about that in chapter 1, how to find the not find the domain, how to solve inequalities that had rational structure. Remember we found our crumbers, critical numbers, and then did the intervals. So here's what we do. You set the top equal to 0, you find the first critical number. It ends up being 3 over 4. And it's bracketed because it's the 0 up top and we have an equal to. If you set the bottom equal to 0, you get x equals 1 as your other critical number. They get parentheses because you can't divide by 0. The parenthesis means don't include. All right, I think we have... Talking is tough right now. I think we have enough info to set up our intervals. So negative infinity, start there. Go to 3/4. Stop, bracket, start again at 3/4. Stop at 1, and then go 1 to infinity. All right, at this point, we just test some value in between. So 0, 3/4. So 3/4 is smaller than 4/5, which isn't quite 1. And then 1 to infinity, check 2. Now we are plugging into this inequality right now, and we're just trying to determine, since it's greater than or equal to 0, which one of these yields a positive number. So we plug in 0 for the x's. Long story short, just because the video, it's running right now, and we're already at 11 minutes, 40 seconds. This one becomes a positive when you plug everything in, which is what we want. This is a negative, which is not what we want. And this is a positive, which is what we want. So the domain of this function, okay, is negative infinity to 3/4 with a bracket, in union with, remember that U symbol, 1 to infinity, both parentheses. All right, third and final examples. There's 3 parts. We are putting into the f function g of x, which is x squared. So f of x squared just means plug in an x squared in place of the x. There's my composite. It's underneath the square root, so I need to say it's greater than or equal to 0. By the way, when considering the domain, remember, this is a parabola, which means it has no boundary to its domain. This is negative infinity to infinity, so whatever our answer is for the composite, that's our domain for the whole thing. You can find critical numbers here, but remember, you've got a geometric approach to this as well. I'm thinking x squared minus 8 is basic enough to where we should be able to graph that thing. It's a regular parabola centered on 0, 0 that shifted down 8 units. So if you go down to negative 8, your parabola opens upward like this, because we know it's a 1x squared, that means it goes upward. Where is this parabola greater than or equal to 0? Is asking the question, where does our parabola exist above the x-axis? Well, it's from negative infinity to this 0. And then it's this 0 to infinity. So we don't even really need to test our intervals. We just got to find the zeros and then plug them in right there. So where does x squared minus 8 equal 0? Well, you can add 8 to both sides. You square root both sides. Remember, if there's an x involved, you are going to square. You're going to have a plus or minus there. It ends up being 2 root 2, which is something close to like 2.828-ish, something like that. You can use the decimals. I'm going to stick with the exact values here. You'd use a bracket. And that's the solution right there. Now, if you wanted to go the traditional route, you could say x equals 2 root 2, and x equals negative 2 root 2 are our critical numbers, or as I affectionately call them, crumbers, and you can set up these intervals. Hello. You can test them by plugging them into this expression. X squared minus 8 is greater than or equal to 0. So test, 0, test negative 3, test positive 3. And it's pretty simple to see that. 0 squared minus 8 is negative. But if I square 3 and get 9, that's going to be positive. If I square negative 3, I still get 9, and it's going to be positive as well. So these are the two components to the domain for this. But as I said, you could use a geometric interpretation to bypass all that algebraic work. So, in case I wasn't clear, here's the domain. Those two. All right, g of f of x just reverses things. So hold on, let me freeze this so I can go back and see what the functions were. Is it g of f? So g of f of x. Oh, I'm plugging the square root function into the parabola function. You're just squaring it. Oh. Doesn't the square just get rid of the square root? Well, that was easy. There's my composite function. What's the domain of it? Well, here's where I get most students. They see that and they're like, oh, it's a polynomial. All real numbers. Wrong. The input function was root x minus 8, which means it was structurally bound to x minus 8 greater than or equal to 0. Hey, look, it's got to be greater than or equal to 8. So wow, that was a bad 8. Even though this looks like all reals, none of the numbers that you can plug in here are less than 8. So that's our domain. Our domain is 8 to infinity. All right, last thing, h of k. And it's a good thing it's our last thing because this video is topping 18 minutes. You guys got stuff to do. All right, h of k. Darn it, what is the function? Sorry, guys. Very unprofessional of me. H of k. Oh, these aren't too bad. H of k of x. Our k is 3x minus 1. Our h is just 1 over x. Domain. The input looks pretty clean to me. That's a linear function that really has no problems, so we're going to say the input function has a domain of all real numbers. Our composite function can't equal 0 on the bottom, so x cannot equal 1/3. I'm just letting you guys do the mental math as I did right there. 3x minus 1 cannot equal 0 at 1/3. So, our answer? All reals except x can't be 1/3. All right, I hope this was enormously helpful for you guys to just totally piece together function composition in tandem with domain so that you guys are moving forward very confidently. All right, thanks for watching.